This conference will now be recorded.
All right, this is the problem solving section that we started in class, and I'm looking to do a few extra ones on this video so that you guys, when we get together, we'll only do maybe one or two more before we start reviewing for the test. So we did number one together in class. I'm going to go ahead and do number two. It says a consulting engineer's time is billed at $60 per hour, and her assistant is billed at $20 per hour. The customer received a bill for $580 for a certain job. If the assistant worked 5 hours less than the engineer, how much time did each bill on the job? So we have an engineer and their assistant, and it looks like their amount of work that they're doing is kind of being related to each other. So the first thing I want to do is write out just kind of what we're looking for. So time for engineer and the time worked for the assistant. So it says if the assistant worked 5 hours less than the engineer. So think about the engineer just being a plain old X. Then less than that would be minus. So X minus 5 would be the assistant's. The engineer gets billed at $60 per hour and the assistant gets billed at $20 per hour, and we know the total bill was $580. So $60 for the engineer plus $20 for the assistant per hour equals the 580. So this is 60x plus 20x minus 100, if I distribute, equals 580. That's 80x. I'm going to add the 100 over and get 680. So I'm dividing 680 by 80. And that is 8.5. Now that is just for X. That's the engineer. So that means that the engineer worked 8.5 hours on this job. And it did ask us for both times, so how much time did each bill on the job? So the assistant would have done 5 hours less than that, so 3.5 hours. So there are both of the things we were looking for. Okay, the next one I want to do for you guys is I want to do a mixture problem. And like I said, we'll do the other one in class, so I'm kind of saving one for us to do together. So in a mixture problem, usually what's happening is we have two different concentrations of something like acid or special medicine. They're trying to add them together to create a final product. So I kind of think of it as a bucket problem. So a pharmacist to prepare 15 milliliters of special eye drops for a glaucoma patient. So normally they don't have just exactly what they need on hand, they have common percentages. The eye drop solution needs to be 2% active ingredient. So they know that the final product should be 15 milliliters of the eye drop, and it should have 2% of the ingredient. The pharmacist only has two in stock, though. They have a 1% active ingredient and a 10%. And the question is, how much should each of these boxes be so that it kind of melts down to a 2% mixture? So obviously, common sense would tell you we need a lot more of the 1 than we do of the 10 because we just barely want to bump up to 2%. So that kind of helps you know if your answer at the end is right, if you just kind of think about that, which one is closer to the final bucket. So what we do in these, we have to realize this has to add up to 15. You can't have more medicine than you're going to give the patient because if you don't give them all of it, the concentration's not right. So we're going to let this box just be X because we don't have a name for it. You could call this Y, but we haven't learned two variable systems in this class and we don't focus on those. So we're going to call this 15 minus X because if this was 5, this would have to be 10. It has to add up to 15. So then the next step is, now some people will ask, do I need to convert these all to decimals before I do my equation? If they're all percentages, you don't have to, but if even one of these was not a percent, which would be weird in a mixture problem, then yeah, you would need to convert any percents to decimals. But since they're all percentages, we can just multiply. So it's 1x, that's the percent of the concentration times the quantity, plus 10 times this quantity, equals 2 times 15. So that's a 2. So then we multiply this all out. So this is x plus 150 minus 10x equals 30. That's a negative 9x plus 150 equals 30. We would subtract over the 150, so negative 9x equals negative 120. And they're both negative, so when I divide, it's going to be positive. I'm getting 13.33. We're going to round to 2 decimal places since they didn't specify. So that's milliliters of the 1% solution. It said how much of each type do we need? So 15 minus the 13.33 will tell us the other one. So I'm just going to subtract backwards. So it's 1.67 milliliters of the 10%, which kind of makes sense. You would only need a tiny bit of that 10% solution to up your concentration of your 1% solution. We'll do the asthma medicine one together in class. So I want to do what's called a work rate problem next. So with water from one hose, a swimming pool can be filled in 8 hours. A second larger hose alone can fill the pool in 5 hours. How long would it take to fill the pool if both hoses were used simultaneously? So this is what we call a work rate problem, and the two objects, or here the hoses, are working at different rates. The smaller hose, since they said the second one was larger, so the small hose takes 8 hours to do one job, which is to fill the pool. The large hose by itself takes 5 hours to do that same one job. The question is, if they work together, that would be X hours, and it would still be that one job. The problem is when we want to compare these to each other, we need to know how much of the job are they completing in 1 hour. So the way you can do that is you can divide over the time. So this would be 1/8 of the job per hour. And we do this because the rate is not the same that they're working. And we need it to be a single unit of per hour. 1/5 of the job per hour. And then this would be 1/x of the job per hour. So now everything is related to 1 hour of work. So what happens in 1 hour of work is that if you had the two hoses both going, you would add them together. So 1/8 plus 1/5, because those are the solo hoses individually working. And we would hope that would equal the combo. So then I noticed that the LCD here is 40x, because there is an x down here. So if we multiply everything by 40x, that would be 5x plus 8x equals 40. That's 13x equals 40. Divide by 13. So 40 divided by 13 is 3.1 if we go to 1 decimal place. So it'll take approximately 3.1 hours for the two hoses to do the job together, which makes sense. If they're both working on it, it should take less time. I don't have another one of these in the notes, but we'll do 1 or 2 more of those together as well. So this last one's just really an application to the real world. Donnie bought a shirt at 35% off. He paid $17.55 for the shirt. What was the price of the shirt before the discount? So you have this thing called sales price when you have something on sale, and it's always the original price minus the discount. A discount is always the original price at a percent. So it's a percent times the original price. So we know he paid 30% off, and he got 35% off, and he paid $17.55 for the shirt. So that's actually the sales price. We don't know the original, and that means we don't actually know the discount yet, because it would have been 35% of the original price, which we're calling X. So this is $17.55. Remember, that's a 1. So 1 minus 0.35 is 0.65x. And if we divide by 0.65, in other words, we're figuring out if he got 35% off, then we're thinking of it as he only paid 65% of the original. So 17.55 divided by 0.65, the original shirt cost $27. So 27 was the original price. All right, and that's the end of this video.